Some comets tumble, others flare, but 3I Atlas just did something no comet should ever do. It hit the brakes. On its way to the sun, this thing stopped. It vented gas toward the sun like it was fighting gravity itself. Then weeks later, it changed its mind. It flipped, firing its jets the other way, and started accelerating again, like a spacecraft waking from silence. Before you click off and think, this is rubbish, hear this. We have the images. Right now, on your screen. Proof. Let me explain. This first image, from the Hubble Space Telescope on July 21st, 2025. See that? The tail is pointing at the sun. A sun-facing spike. Astronomers call it an anti-tail. It defies every law of comet behavior we know. Now look at this, weeks later, from the Nordic Optical Telescope. The same object, but now its tail streams away from the sun, like every well-behaved comet should. Between these two moments, something changed. Something that shouldn't be possible. This wasn't a viewing angle trick. It wasn't an illusion. The scientists have ruled all that out. This was a physical reversal, a jet inversion. If this was a controlled maneuver, if someone or something just used our sun as a slingshot, then everything changes. We have weeks, not years, to find out. It reaches its closest point to the sun on October 29th. That's the moment of truth. This is real. This is happening now. And I need to know, are you seeing this? Where are you watching from right now? What time is it there? Tell me in the comments. This story is unfolding in real time. Hit subscribe so you don't miss a single revelation. You are the reason we can keep following the impossible. And for that, thank you. Let's get to work. The evidence for the anomaly of 3I Atlas is most starkly presented in a direct, visual comparison, a tale of two images that has sent ripples of disbelief and excitement through the global astronomical community. The first image, a pristine capture from the Hubble Space Telescope on July 21st, 2025, shows the comet as a brilliant, fuzzy star set against the black velvet of space. But its most prominent feature is all wrong. Instead of a tail streaming away from the sun, pushed by the relentless solar wind, it displays a sharp, sunward-pointing spike of light, a luminous dagger aimed directly at the heart of our solar system. This structure, known as an anti-tail, is a rare and perplexing phenomenon that challenges simple explanations. The second image, taken mere weeks later by the steadfast Nordic Optical Telescope, shows the same object, but the cosmic order has been restored. The comet now sports a magnificent classic tail, billowing elegantly away from the sun, exactly as every well-behaved comet since the dawn of humanity should. Between these two moments, something fundamental and physical changed within 3I Atlas. It is tempting to dismiss this as the erratic behavior of a typical comet. They are, after all, known for their unpredictability, brightening, fading, fragmenting. We have chronicled their celestial ballet for millennia, but this is categorically different. This is not a change in brightness or a breakup event. This object appears to have physically reversed the very direction of its material emission. In July, it was actively spewing gas and dust sunward, an action that, according to Newton's third law, would create thrust acting as a brake on its orbital motion. Then, as summer turned to fall, that forward-facing emission systematically faded, and a new, powerful jet of material grew in the exact opposite direction, providing acceleration. The immediate skeptical thought is that this is a trick of perspective, an illusion born from Earth's own changing position in its orbit around the sun. We see these projection effects frequently in astronomy. A galaxy that looks edge-on from one vantage point can appear face-on from another. It is all about one's seat in the cosmic theater. However, the international teams of scientists tracking 3I Atlas have run the complex geometric calculations, and the timing is definitively wrong for a pure projection effect. The composition of the material being shed was observed to change between the two periods. The morphology, the technical term for the shape and structure of the tail, evolved in a way that points to an intrinsic physical change deep within the comet's core. This was not a sudden, instantaneous flip, but a slow, deliberate transition over several weeks, a gradual reversal that played out as the comet continued its hyperbolic plunge toward the inner solar system. It is this controlled, gradual nature that elevates the event from a curiosity to a profound enigma, demanding an explanation that stretches beyond our current understanding of cometary physics. To fully appreciate why the jet inversion of 3I Atlas is so revolutionary, we must delve into the fundamental physics governing a comet's journey through the solar system. When a comet vents material, gas and dust into the vacuum of space, that act is not passive. It carries momentum and it creates thrust. In essence, a comet functions like a poorly controlled rocket engine. If you are ejecting mass toward the sun, you are creating thrust in that direction, effectively applying a brake to your forward orbital motion. Conversely, if you flip that jet to point away from the sun, you are now firing a rocket that accelerates you, adding to your orbital velocity. For any object on a precisely calculated trajectory through the solar system, governed solely by gravity, such a significant reversal in thrust direction should leave an indelible mark on its path. Its orbit should measurably deviate from the perfect gravitational arc predicted by the equations of Newton and Einstein. The object should be in a slightly but detectably different position than where pure celestial mechanics says it should be. This deviation is known as non-gravitational acceleration, and it is a well-documented and routinely measured effect in active comets, a testament to the rocket-like effect of their outgassing. But here we arrive at the very core of the 3i Atlas puzzle, the detail that elevates it from merely strange to profoundly enigmatic. 3i Atlas is showing minimal to no non-gravitational acceleration. Its path through the solar system matches, within the tiny margins of measurement error, what gravity alone would dictate. This stunning absence of recoil forces us to consider a set of possibilities, each more staggering than the last. The first possibility is that the jets are perfectly balanced, firing material in all directions simultaneously so that the net thrust vectors cancel out to nearly zero. For a natural, irregularly shaped body tumbling through space, this is a statistical near impossibility, akin to a fire hose spraying chaotically, yet producing no net force on the firefighter. The second possibility is that the object is so incredibly, unimaginably massive that the recoil from its outgassing is negligible, like the push of a fly on a battleship, present in theory but undetectable in practice. The third possibility, the one that fuels both scientific debate and public imagination, is that something else entirely is happening, a process we have not yet considered, or a technology that expertly mimics natural outgassing while carefully controlling its net effect on the trajectory. The visual evidence is compelling. Imagine arrows or vectors superimposed on the time series images, showing the direction of material ejection. In July, the arrow points defiantly sunward. Through August and into September, that arrow fades and a new one grows, pointing precisely away. When astronomers correct for all possible viewing angles, for all potential projection illusions introduced by Earth's orbital motion, the reversal remains a physical fact. Something real and fundamental changed about how this object was propelling itself through the void of interplanetary space. Before leaping to conclusions that sound like they are lifted from science fiction, it is essential to give the natural universe its due. Physics, in its infinite and often counterintuitive complexity, frequently has a logical explanation, and the most conservative and scientifically favored one for 3i Atlas has been rigorously developed by astronomers like Avi Loeb and Andrew Keto. Their model is elegant and persuasive, relying entirely on the well-understood behavior of different ices sublimating at different temperatures. Imagine the nucleus of 3i Atlas not as a homogeneous ball of ice, but as a layered onion, forged in the protoplanetary disk of an alien star system billions of years ago. The outer layers, exposed to the harsh radiation and near absolute zero temperatures of interstellar space for eons, would be rich in highly volatile ices, with carbon dioxide, CO2, being a prime candidate. CO2 ice sublimates, transitions directly from solid to gas at very low temperatures, becoming active even in the chilly depths beyond 3 or 4 astronomical units from the sun. As this carbon dioxide erupts into space, it drags with it an entrained flow of tiny, ice-coated dust grains. These small grains are exceptionally efficient at forward-scattering sunlight. Under the specific viewing geometry from Earth in July, this efficient forward scattering could have created the intensely bright, compact, and apparently sun-facing anti-tail observed by Hubble. Now, as the comet continues its relentless plunge closer to the sun, its surface heats up. The carbon dioxide-rich outer layers are eventually depleted, stripped away by the escalating sublimation. The active sublimation front, the zone of violent phase change, digs deeper into the nucleus, penetrating a new stratum dominated by water ice. Water ice is more refractory. It requires significantly more heat to activate and becomes the dominant outgassing driver in the warmer inner solar system. The dust released by water ice sublimation is different, typically larger, more refractory, rocky, and less icy. These particles do not forward scatter light as efficiently. Instead, they are more susceptible to solar radiation pressure, the gentle but persistent push of sunlight, which sculpts them into the classic curved dust tail streaming away from the sun. The timing in this model aligns almost perfectly with the observations. The antitail was most prominent when 3I Atlas was around 3 to 4 AU from the sun, precisely the distance range where CO2 sublimation should be most active, while water ice remains mostly dormant. The observed tail reversal occurred as the comet descended through 3 AU, heading toward its October perihelion at 1.356 AU, exactly the transitional period where the shift from carbon dioxide-dominated to water-dominated activity would naturally occur. This explanation is the one most comet scientists would favor. It is parsimonious, requiring no new physics, no exotic assumptions about alien technology. It posits that 3I Atlas is a fascinating but ultimately natural interstellar comet, with a specific and unusual compositional stratification, offering us a unique glimpse into the formation processes around other stars. Yet, despite the elegance of the compositional transition model, not everyone in the scientific community is convinced that it tells the complete story. We now venture firmly into more speculative territory, but we do so with a scientist's rigor and a commitment to following the evidence, not a tabloid's breathless sensationalism. Abraham Loeb, joined by other researchers like Adam Hibbard, has persistently raised the question that most mainstream astronomers cautiously avoid. What if the jet reversal of 3I Atlas is not a passive, natural process at all? What if it is the signature of a controlled maneuver? An intentional trajectory adjustment using a propulsion system that only superficially resembles the random outgassing of a comet. This engineered probe hypothesis rests critically on the precise timing, directionality, and context of the observed events. Consider the sequence. If the sun-facing antitail observed in July was, in fact, a directed braking thrust, slowing the object down as it fell sunward, and the subsequent anti-solar tail was a forward thrust, accelerating it as it prepared to swing around perihelion, then the entire sequence bears an uncanny resemblance to a trajectory correction burn, the kind an intelligent operator would program into a spacecraft to fine-tune its gravitational slingshot maneuver around a star. Before dismissing this as fantasy, it is crucial to consider the specific, observable signatures that would support such a hypothesis. First would be the presence of sustained, directional, non-gravitational acceleration that defies all models of sublimation-driven thrust in its magnitude, duration, or timing. Second would be repeatable, arbitrary reorientations of the jet axis that show no correlation with the comet's natural rotation period or the pattern of solar heating across its surface. Third would be clear spectral anomalies, the detection of emission or absorption lines indicating materials wholly inconsistent with the primitive ices and dust expected in a natural comet, refined metals or complex molecular compounds suggestive of manufacturing. To date, it must be emphasized, none of these definitive smoking gun signatures have been conclusively observed. The data remains incomplete, the object is faint and fast-moving, and continuous monitoring is challenging. However, as the old adage goes, the absence of evidence is not evidence of absence. Testing the engineered object hypothesis requires long-term, ultra-precise astrometric monitoring, measuring the object's position repeatedly over months and years, then fitting those positions to orbital models with and without non-gravitational terms. The residuals, the tiny but systematic differences between the predicted and observed positions, could reveal the telltale signature of a sustained, directed thrust that natural outgassing could not produce. The broader scientific community's reaction to this hypothesis has been overwhelmingly mixed, leaning heavily toward justifiable skepticism. The history of astronomy is littered with tantalizing anomalies that were later resolved into entirely natural, if complex, phenomena. Pulsars were once seriously considered as potential alien beacons. The null hypothesis that 3I Atlas is a weird but natural comet carries a strong prior probability. Yet, Loeb and his collaborators argue compellingly that dismissing the possibility without rigorous testing is itself an unscientific act. They point to a critical asymmetry. The cost of a false negative, missing a genuine techno signature because we were too cautious or dismissive to look, is arguably Civilizationally, far higher than the cost of a false positive, spending time and resources studying a natural object we briefly thought might be artificial. To move beyond speculation and ground the mystery of 3I Atlas in hard physical reality, we must confront the numbers, and the quantitative constraints tell a story of almost unimaginable scale and profound puzzle. Between July and October of 2025, meticulous analysis of the comet's brightness and gas emission lines revealed that 3I Atlas shed approximately 2 million metric tons of material into the void. Let that figure resonate for a moment. 2 million tons. That is the equivalent mass of 3 Empire State Buildings, completely vaporized and cast into the vacuum of space over just a few short months. Astronomers derived this staggering figure through careful photometry and spectroscopy, measuring how much sunlight was being scattered by the dust and absorbed and re-emitted by the gas, then applying complex conversion factors that account for particle size, reflectivity, and geometric distribution. This immense mass loss must, by the ironclad laws of physics, create thrust. Newton's third law, for every action, there is an equal and opposite reaction, is as immutable in the depths of interstellar space as it is in a physics classroom on Earth. Every kilogram of material ejected from the nucleus pushes back on it. For the vast majority of active comets, this rocket effect is not just theoretical. It is directly measurable as non-gravitational acceleration, causing their orbits to deviate from purely gravitational paths. But for 3I Atlas, this expected signature is conspicuously, bafflingly absent. Its trajectory is, within the tight margins of observational error, purely gravitational. This profound absence of recoil places a powerful and inescapable constraint on the object's fundamental properties. The calculation is straightforward in principle. If you know the rate at which mass is being ejected, the mass flow rate, and you can estimate the velocity at which that material is leaving the nucleus, the exhaust velocity, you can calculate the thrust force using the fundamental rocket equation. Then, to explain why that substantial thrust force is not producing a detectable acceleration, you can calculate the minimum mass the nucleus must have to resist the push. The result of this calculation is, once again, staggering. The lower limit estimate for the nucleus mass comes out to approximately 33 billion metric tons. The uncertainty bands are considerable due to unknowns in the exact dust-to-gas ratio and ejection velocities, but even on the most conservative end, we are dealing with an object weighing tens of billions of tons. For context, the legendary comet Hale-Bopp, one of the most massive comets ever observed, was estimated at about 60 billion tons. 3I Atlas is, by any measure, a substantial body, likely several kilometers in diameter. This immense mass is one plausible reason its outgassing has not significantly perturbed its orbit. The thrust is simply too small compared to the object's immense inertia. However, it also raises a secondary, more subtle question. If it is so massive and shedding material at such a ferocious rate, why is the resulting thrust so perfectly balanced as to produce no net directional nudge? Is this due to a miraculously symmetric outgassing pattern across its surface? Or could it be the result of a controlled, engineered process designed to minimize detectable trajectory changes outside of intended maneuvers? The numbers do not prove the latter, but they certainly keep the question alive and burning. All the models, the debates, the speculations, and the complex orbital calculations lead to a single defining moment: perihelion. On October 29, 2025, 3I Atlas will reach its closest point to the Sun, at a distance of 1.356 astronomical units, approximately 203 million kilometers from the solar surface. This passage is the crucible, the moment of maximum heating, maximum stress, and maximum activity. The Sun's ferocious radiation will batter the nucleus, driving temperatures to their peak and potentially triggering violent, fresh outgassing from previously dormant or shielded regions. If 3I Atlas is a natural comet, as the compositional model suggests, we should witness a dramatic increase in its activity. It could become vastly brighter, its tail could lengthen and complexify, and it might even undergo fragmentation, as comets often do under such extreme thermal and gravitational stress, which would serendipitously reveal its internal structure and layering. If, however, it is something else, if there is any merit to the engineered object hypothesis, the close solar passage might act as a trigger for systems that have remained dormant during the cold, quiet approach from interstellar space. It could be the moment its true nature is unmasked. The observational challenges during this critical period are immense. As it rounds the Sun, 3I Atlas will be positioned close to the Sun in the sky as seen from Earth, visible only in narrow windows during morning or evening twilight. The Hubble Space Telescope, which captured the first iconic image of the anti-tail, operates under strict solar avoidance constraints. It cannot point anywhere near the Sun without risking catastrophic damage to its sensitive instruments. Ground-based telescopes must contend with the blurring effects of Earth's atmosphere and the limited observing time during twilight. However, a potential wildcard exists: the planet Mars. On October 3rd, 3I Atlas made a relatively close flyby of the red planet. The critical question is whether the high-resolution cameras aboard orbiters like the Mars Reconnaissance Orbiter, specifically the HiRISE instrument, capable of resolving features less than a meter across on the Martian surface, were tasked to image the passing visitor. A single image from HiRISE, captured from a completely different vantage point than Earth, would be invaluable. It would provide a starkly different perspective on the comet's coma and tail structure, helping to break the degeneracies inherent in interpreting three-dimensional structure from two-dimensional Earth-based projections and potentially settling the debate between intrinsic activity changes and simple projection effects. The real scientific payoff, however, will come in the weeks and months after perihelion. As the comet swings back outward on its hyperbolic escape trajectory, its brightness will initially remain high due to the fresh outgassing triggered by the solar encounter. This is the period when astrometry, the precise, repeated measurement of its position, becomes absolutely critical. Any deviation, however slight, from its pre-perihelion gravitational orbit will be a monumental discovery. The sudden appearance of clear non-gravitational acceleration, or a change in the magnitude of an existing tiny effect, would tell us unequivocally that the close solar encounter altered something fundamental about the object's outgassing pattern, or its internal dynamics. The clock is ticking down to this ultimate cosmic experiment, and the entire astronomical community is watching, instruments poised, ready to capture every photon. In the rigorous world of observational astronomy, a fundamental and humbling lesson is that not every strange sight in the sky is genuinely strange. Often, the extraordinary is merely the ordinary viewed from an unusual angle, or through an instrument with subtle biases. The apparent retrograde motion of Mars confused ancient astronomers for centuries, until the heliocentric model revealed it as a simple perspective effect. The canals of Mars turned out to be optical illusions, the human brain connecting random surface features into non-existent patterns. Many comets throughout history have appeared to display bizarre tail orientations or sudden brightenings that later resolved into geometric or instrumental artifacts. Therefore, the paramount question facing the 3I Atlas investigation is brutally simple. Are we witnessing an intrinsic jet reversal, a real physical change on the object, or are we being fooled by a sophisticated projection illusion? The distinction is everything. An intrinsic flip demands a revolutionary physical explanation, something changing inside the comet or on its surface. A projection effect is merely celestial geometry, Earth's motion relative to the comet, creating an apparent reversal in the sky, while the actual three-dimensional pattern of material ejection remains constant. The science of projection effects is well developed. We observe a comet's complex three-dimensional coma and tail as a two-dimensional projection on the celestial sphere. Our line of sight collapses depth information, making it extraordinarily difficult to distinguish between material moving directly toward us, away from us, or perpendicular to our view. As both Earth and the comet move along their independent trajectories, the viewing geometry constantly shifts. A jet that appears to point in one direction can seem to flip 180 degrees as our perspective changes, even if the jet itself remains fixed in space. The classic example is the anti-tail phenomenon, understood for over a century. When Earth's orbit carries it through the orbital plane of a comet, large, slow-moving dust grains that lag behind the nucleus along its path can appear, from our edge-on viewpoint, to project as a sunward-pointing spike. These particles are not moving toward the sun. They are simply trailing behind the comet in its orbit. Then, as Earth moves out of the orbital plane, this illusion vanishes, and the normal tail becomes prominent again. The astronomers, from the Nordic Optical Telescope team who tracked 3I Atlas through its transition would have been acutely aware of these pitfalls. Their published conclusion that an intrinsic jet reversal occurred strongly suggests their sophisticated geometric modeling ruled out a pure projection effect as the sole explanation. However, such modeling requires assumptions about the dust grain size distribution, their ejection velocities, and their survival times. Uncertainty in these parameters always leaves a sliver of doubt, a window for an alternative, purely geometric explanation. The abruptness of the observed transition, occurring over weeks rather than smoothly over months, argues against a simple projection effect, which would typically be more gradual. Furthermore, and critically, projection effects cannot change the chemical composition of the emitted material. Reports from spectroscopic follow-up indicate that the relative strengths of different molecular emission lines did shift between July and September, supporting the physical transition model from carbon dioxide to water-dominated outgassing. This compositional change is intrinsic, not geometric. While projection likely played a role in the specific appearance and brightness of the features, the consensus among those who have analyzed the full dataset is that a real physical change occurred within 3I Atlas, a conclusion that forces us to confront the anomaly at its face value and seek a physical explanation, be it natural, exotic, or otherwise. The key to unlocking a comet's visual appearance often lies not in the grand sweep of its orbit, but in the microscopic properties of the dust it ejects. Not all dust grains are created equal, and their inherent inequality, their size, composition, and shape, dictates the grand sweeping structures we see through our telescopes. The critical parameter in this dusty drama is the beta parameter, a dimensionless number that captures the ratio of solar radiation pressure to solar gravity acting on an individual dust grain. Tiny sub-micron grains have a high beta value. The push of sunlight overwhelms the pull of solar gravity. Once freed from the comet's nucleus, these tiny particles accelerate rapidly away from the sun, forming the straight, finely structured ion or dust tails that can stretch for millions of kilometers. Larger grains, tens or hundreds of microns across, the width of a human hair, have a low beta value. They barely feel the light's push and are dominated by gravity, following paths much closer to the comet's own orbit. These large, sluggish particles form broad, diffuse dust trails that lag behind the comet, often tracing its orbital path around the sun. Under very specific viewing geometries, when Earth crosses through the plane of this dust trail, this population of large, low-beta grains can appear to project as a sunward-pointing feature, the classical geometric anti-tail. It is not real, emission toward the sun. It is a line-of-sight effect, a celestial mirage. This is the purely physical, non-exotic explanation for what the Hubble Space Telescope might have seen in July. We were simply looking edge-on at a trail of large dust particles that 3I Atlas had shed earlier in its journey. However, the Loeb and Keto compositional transition model proposes a different, more nuanced mechanism. They suggest the initial sun-facing glow was not from large lagging grains, but from a profusion of small, icy grains, freshly released by vigorous carbon dioxide sublimation. These small grains are brilliant forward scatterers of light. From Earth's specific viewing angle in July, this intense forward scattering could have created a compact, intensely bright, sun-facing feature, a real enhancement of emission in that direction, amplified by our perspective, not a projection of trailing material. Then, as the comet's activity regime shifted to water and refractory dust, the dominant grain population changed. The new particles were larger, darker, and less efficient at forward scattering. This caused the sun-facing brightness to fade, while the classical backscattering off the large grains in the anti-solar tail grew more prominent, creating the observed reversal. The truth of what happened with 3I Atlas likely involves a complex and dynamic interplay of both genuine changes in emission properties, the compositional transition, and subtle geometric projection effects. However, the observed brightness, contrast, the spectral shifts, and the specific timing of the transition collectively push the boundaries of what dust physics and projection alone can comfortably explain. This lingering tension is what keeps the door open to more profound interpretations, and fuels the continued, intense scrutiny of this mysterious visitor. In the modern era of astronomy, truth is never derived from a single source. It is built patiently, painstakingly, through a robust web of cross-checked observations from diverse instruments, each with its own unique strengths, weaknesses, and potential systematic errors. For 3i Atlas, this global network has been essential in confirming the reality of the anomaly. The web includes the Hubble Space Telescope, providing pristine, space-based clarity free from atmospheric distortion. The Nordic Optical Telescope, offering the flexible, sustained monitoring crucial for tracking temporal changes, and large ground-based observatories like Keck in Hawaii and Gemini in Chile, capable of the difficult task of high-resolution spectroscopy on a faint, fast-moving target. Each of these facilities faces its own distinct challenges. Hubble must execute complex tracking to avoid smearing its images of the fast-moving comet. Ground-based telescopes battle the ever-present blurring of atmospheric turbulence, though adaptive optic systems can partially compensate. Spectroscopy is particularly demanding, requiring the precise alignment of a narrow slit on the comet's fuzzy coma to disperse its faint light into a rainbow of chemical information, all while the target is moving against the background stars. Calibrating the absolute brightness of a diffuse, irregularly shaped comet is notoriously subjective and prone to systematic differences between observatories. Yet, when multiple independent systems, operating on different principles and in different locations, see the same phenomenon, confidence soars. The fact that both Hubble and the Nordic Optical Telescope, along with other facilities, independently observed the sun-facing anti-tail in July and its subsequent fading and replacement by a classical tail, means this was not an instrumental artifact or a local atmospheric effect. It was a real celestial event. The James Webb Space Telescope, JWST, represents a potential game-changer in this web, though its involvement is not guaranteed. JWST's supreme infrared sensitivity is perfectly suited for detecting the fundamental vibrational bands of key cometary molecules like water, carbon dioxide, and carbon monoxide. If directors' discretionary time can be allocated, JWST could deliver a definitive quantitative compositional analysis, settling the debate between the CO2 to water transition model and any potential spectral anomalies that might hint at unnatural constituents. Its data would provide the final authoritative word on the comet's volatile inventory. This coordinated global effort, spanning space-based and ground-based assets, combining imaging, photometry, and spectroscopy, is modern astronomy at its very best. It is a community-wide enterprise, a collective exercising of our sensory and analytical capabilities to interrogate a mystery from the depths of space. No single instrument tells the whole story, but together, cross-checked and calibrated, they build a dataset robust enough to distinguish a true cosmic anomaly from mere observational illusion. The investigation into 3i Atlas is not a purely abstract exercise in data analysis. It is a profoundly human endeavor, fraught with all the complexities of ambition, reputation, institutional politics, and the deep-seated desire to be the one who unlocks a fundamental truth. The controversy surrounding the object is intensely magnified by what can be termed the Loeb effect. Abraham Loeb is no ordinary astronomer. A former chair of Harvard's astronomy department, a prolific author, and a public intellectual who engages with media and the public with an enthusiasm most academics carefully avoid. He occupies a unique and influential position. He has built a reputation for championing bold, speculative hypotheses, most famously with Oumuamua, which he suggested could be a light sail, an artificial artifact from an extraterrestrial civilization. His advocacy has sharply divided the scientific community. Some colleagues appreciate his willingness to challenge conventional thinking and his forceful argument for taking the search for techno-signatures seriously, a field that has long struggled for funding and mainstream acceptance. They see him as a necessary provocateur, pushing the boundaries of what is considered legitimate scientific inquiry. Others, however, worry deeply that his high-profile, premature speculation undermines the credibility of astronomy as a whole, making the field appear frivolous to funding agencies and the public, and potentially damaging the careers of younger scientists associated with such ideas. The media ecosystem, predictably, amplifies the most sensational angle. A nuanced scientific paper titled Potential Compositional Transition in 3i Atlas can easily become a headline screaming, "Scientists think new comet could be alien spacecraft." Context and caveats are stripped away, and the complex, probabilistic nature of scientific discourse is reduced to a binary, click-driven question: alien or not? This creates a tension between open-minded inquiry and the very real risk of public disillusionment if the exotic claims later prove to be false. Loeb's defenders argue that the potential payoff of discovering extraterrestrial technology is so monumentally consequential for humanity that it justifies exploring even low-probability hypotheses with rigor and resources. They point to an asymmetry. The cost of a false negative, missing a real techno-signature, is incalculably higher than the cost of a false positive, wasting effort on a natural object. The saga of 3I Atlas is thus not just a story about physics and observational data. It is a compelling case study in the sociology of science. It reveals how scientific truth is negotiated not only through telescopes and equations, but through the personalities, institutions, funding pressures, and communication strategies of the humans who interpret the cosmos. How the community navigates this high-stakes controversy will set a precedent for how future, equally ambiguous anomalies are handled. Let us, for a moment, fully entertain the impossible. Let us imagine a future, months from now, after the perihelion passage and the Earth-close approach, when all the data is in, every natural model has been tested to destruction and found wanting, and the international scientific community slowly, reluctantly, reaches a consensus. 3I Atlas is not a natural comet. It is an artifact. What would that world-altering proof actually look like? The standard of evidence would need to be almost inconceivably high, far beyond the standard for a typical astronomical discovery. It would require not one, but multiple, independent, and converging lines of evidence, each one strong on its own, but together forming an overwhelming, undeniable case. The first and most critical line would be sustained, directional non-gravitational acceleration that no model of sublimation-driven thrust can explain. This would not be small. Random orbital residuals within error bars, but clear. Systematic deviations showing the object is accelerating in a specific direction for a duration that contradicts thermal models. For instance, continued thrust long after it has moved far from the sun and should have frozen solid. Or discrete, on-off bursts of acceleration resembling rocket burns rather than continuous outgassing. The second line would be repeatable, arbitrary changes in jet orientation. Natural comets have jets tied to fixed active areas on their rotating nuclei. If 3I Atlas were observed to reorient its primary emission axis multiple times in ways completely uncorrelated with its rotational period or the pattern of solar illumination, it would strongly suggest external, intelligent control over where and when thrust is applied. The third, and perhaps most damning line of evidence would be spectral anomalies, high-resolution spectroscopy from instruments like JWST, or large ground-based telescopes revealing emission or absorption lines from refined metals, unusual isotopic ratios, or complex molecular compounds that have no business in a primitive, unprocessed cometary body would be a massive red flag. The presence of materials indicative of manufacturing would require an exotic explanation, with artificiality being a prime candidate. A fourth line could come from radio or radar observations. An artificial object might emit electromagnetic radiation, either intentionally as a beacon or unintentionally as leakage from internal power or propulsion systems. The detection of narrowband, modulated radio signals, or even just an anomalous thermal radio spectrum would add a powerful piece to the puzzle. One anomaly, like a small acceleration glitch, can be explained away. But if you have anomalous acceleration plus anomalous spectra plus anomalous radio emissions, the coincidences become too great. Invoking multiple, independent, and unlikely natural explanations becomes less plausible than the simpler, albeit extraordinary, hypothesis: the object is artificial. The verification protocol would be as rigorous as the evidence itself, involving independent confirmation across multiple global observatories, open peer review by adversarial panels, and a statistical significance threshold akin to that used for discoveries like the Higgs boson. The journey to such a conclusion would be the most careful and scrutinized process in the history of science. The timeline for achieving a definitive understanding of 3I Atlas is brutally short, dictated by the unforgiving laws of orbital mechanics. Perihelion on October 29th is the first great milestone, but the next, and perhaps final, critical opportunity for Earth-based observation is December 19, 2025, the date of Earth's closest approach, At a distance of 180 astronomical units, approximately 270 million kilometers, it will be near enough for the most detailed observations our largest ground-based telescopes and, potentially, the James Webb Space Telescope can muster. This is our best and last chance to gather high-signal, high-resolution data before the object begins its long, fading journey back into the interstellar dark. The coordination required to capitalize on this brief window is immense. Global transient alert networks, originally designed for supernovae and gamma-ray bursts, will be activated for this single target. Precious telescope time, scheduled months or years in advance, will be frantically reallocated in real time. The primary bottleneck will be spectroscopy, which requires large telescope apertures and long integration times on a target that is both faint and moving rapidly against the sky. Critical choices must be made about resource allocation. Do we prioritize observations that test the natural comet hypothesis, focusing on composition, dust morphology, and gas production rates? Or do we dedicate a portion of our most powerful assets to the long-shot search for technosignatures, performing deep radio listening campaigns, or searching for unusual polarization signatures? By the time of the December close approach, we will have over a month of post-perihelion data in hand. The object's trajectory will be known with exquisite precision, revealing any non-gravitational forces with far greater accuracy. Its composition will be better characterized, and its post-solar encounter behavior will be documented. The data streams will either converge neatly onto a coherent, natural explanation, almost certainly the compositional transition model, or they will leave us with stubborn, unresolved anomalies that resist all mundane explanations. If it is the former, 3i Atlas will be filed away as a fascinating, exotic, but ultimately understood interstellar comet, a data point in the growing catalogue of galactic wanderers. If it is the latter, the conversation will change overnight. The impetus for a desperate, expensive, and technologically heroic mission to intercept the object will transform from a fringe idea into a serious scientific priority, debated at the highest levels of space agencies worldwide. Even as we chase the departing 3i Atlas, a revolution in how we watch the skies is beginning, a transformation that will forever alter the context of this and all future discoveries. The Vera Rubin Observatory, achieving first light in late 2025, is a machine built for one purpose: discovery on an industrial scale. With an 8.4-meter primary mirror and a staggering 3.2 gigapixel camera, it will image the entire visible sky every few nights in a relentless, decade-long campaign called the Legacy Survey of Space and Time, LSST. This cadence changes everything. Where traditional astronomy often revisits specific targets, Rubin will create a continuous, time-lapse movie of the entire sky. When you compare images taken just days apart, anything that has moved or changed in brightness screams for attention. Asteroids, supernova, variable stars, and comets, including interstellar ones, will reveal themselves by the thousands every single night. The statistical implications for interstellar object science are profound. To date, we have confirmed only a handful: Oumuamua in 2017, 2e Borisov in 2019, and now 3i Atlas in 2025. This is a sample size too small for any meaningful conclusions about their population, typical properties, or origins. Projections suggest that once the Rubin Observatory reaches full operation, it will discover interstellar visitors not as rare events, but at a rate of dozens per year. This abundance will transform the field from anecdotal case studies into a rigorous statistical science. We will be able to construct distributions for their orbits, sizes, activity levels, and compositions. Outliers like 3i Atlas, if it remains one, will be clearly visible against the backdrop of normal interstellar comets. Furthermore, Rubin will provide early warning. 3i Atlas was discovered relatively late in its inbound journey. Future interstellar visitors detected by Rubin will be caught years before perihelion, allowing for extended, planned monitoring campaigns that can watch their activity awaken from dormancy, providing infinitely better constraints on their nature than the snapshot we have of Atlas. The Vera Rubin Observatory is not just a new telescope, it is the usher of a new era, one where the solar system is revealed as a dynamic, bustling crossroads of material from thousands of distant stars. The trickle of discoveries is about to become a flood, and we must be ready to sift through it for the next great anomaly. While terrestrial telescopes track moving objects within our solar system, the James Webb Space Telescope peers outward, its infrared gaze unraveling the mysteries of exoplanets, galaxies, and the early universe. A recent JWST discovery, the detection of a vaporized rock, atmosphere on a searing lava world, exoplanet, showcases the very techniques that could deliver a definitive verdict on 3I Atlas. JWST was able to identify silicon, magnesium, and other vaporized rock components in the planet's atmosphere by analyzing the starlight that filtered through it during a transit. This same powerful technique, known as transmission spectroscopy, could be turned inward, toward 3I Atlas. By taking a sensitive infrared spectrum of the comet's coma, JWST could deliver a quantitative, unambiguous census of its volatile composition. Its instruments are perfect for measuring the fundamental vibrational bands of water, carbon dioxide, carbon monoxide, methane, and complex organic molecules. More importantly, JWST could measure isotopic ratios, the relative abundance of different forms of elements, like deuterium to hydrogen. These ratios are a forensic fingerprint of the temperature and chemistry of the protoplanetary disk in which the comet formed billions of years ago. If 3I Atlas's isotopic ratios match those of solar system comets, it suggests that comet formation is a universal process with similar outcomes across the galaxy. If they differ, it reveals the diverse chemical environments around other stars. For the engineered object hypothesis, JWST's precision is the ultimate arbiter. It could detect spectral features that have no natural explanation, absorption lines from refined metals, signatures of complex polymers, or in complete absence of expected ices. Such a result would be the closest thing to a smoking gun possible from remote sensing. The challenge is one of priority and scheduling. JWST is the most oversubscribed observatory in history. Securing time requires convincing a panel that 3I Atlas represents a unique, time-critical opportunity that outweighs the study of distant exoplanets or the earliest galaxies. The object's potential status as a techno-signature candidate, however remote, provides a powerful argument for allocating precious target of opportunity, time. JWST has the demonstrated power to see what things are truly made of, from hundreds of light years away to within our own solar system. Its data on 3I Atlas could be the final piece of the puzzle, cutting through years of speculation with the cold, hard, and definitive data of infrared light. In a seemingly unrelated realm of astronomy, the LIGO-Virgo-Cagra collaboration continues to listen to the faint ripples in space-time generated by the most violent events in the universe, colliding black holes and neutron stars. While 3I Atlas emits no gravitational waves, the parallel between its investigation and these campaigns is striking and instructive, lying in the methodology of rapid, global, multi-messenger coordination. When LIGO detects a gravitational wave signal, automated alerts are sent out within seconds to a worldwide network of telescopes spanning the electromagnetic spectrum, from radio to gamma rays. These observatories immediately slew to cover the large, poorly constrained region of sky from which the waves originated, searching for the fleeting flash of light that corresponds to the cosmic collision. This multi-messenger approach, combining information from gravity and light, provides a far richer physical understanding than either messenger could alone. The gravitational waves reveal the masses and spins of the merging objects. The light reveals the environment, composition, and explosive aftermath. The intensity of coordination, the rapid decision-making, and the efficient allocation of limited resources under extreme time pressure are a masterclass in modern astronomical operations. This model is a direct blueprint for how we must handle the coming flood of interstellar object discoveries from Vera Rubin. A discovery alert from Rubin will act like a LIGO alert, triggering a pre-planned global cascade of follow-up observations. Smaller telescopes will first confirm the object and refine its orbit. Then, larger facilities will be tasked to perform spectroscopy, astrometry, and photometry, all on a timescale of days or weeks before the target fades or moves out of view. The protocols developed for gravitational wave follow-up, for rapid response, open data sharing, and international collaboration are directly applicable. They teach us the value of having telescopes on standby queue schedules, ready to interrupt their planned observations for high-priority targets of opportunity. They demonstrate the power of immediate open data release to accelerate discovery and engage the global community. The success of gravitational wave astronomy is a testament to what can be achieved when diverse groups agree to collaborate, share resources, and work towards a common goal. As interstellar object science matures from studying individual curiosities to characterizing a statistical population, it will need to adopt a similarly structured, collaborative framework to maximize the scientific return from each fleeting visitor. Just as the need for rapid, large-scale spectroscopic characterization becomes most acute, a new instrument has come online that fundamentally changes the rules of the game. The 4M Multi-Object Spectroscopic Telescope, FMOST, at the European Southern Observatory's Paranal facility in Chile, is not merely an upgrade. It is a transformation of capability. While most high-resolution spectrographs can observe only one, or at best a handful, of objects at a time, FMOST can capture the spectra of 2,400 objects simultaneously. It achieves this through a field of tiny, robotic fiber positioning arms that can independently target stars, galaxies, or solar system bodies across a massive 4-square-degree field of view. This is the difference between studying the ocean with a single fishing rod and dragging a net the size of a city block through it. You will catch everything, including things you never knew were there. The implications for small body science are monumental. The Vera Rubin Observatory will discover tens of thousands of new moving objects every night, but a discovery without characterization is just a set of coordinates. Spectra are needed to know what an object is, its composition, its surface properties, whether it is icy or rocky, primitive or evolved. FMOST provides spectroscopic firepower on an industrial scale. It can conduct massive systematic surveys of asteroid and comet populations, building the vast reference libraries needed to instantly classify new discoveries and recognize true outliers. For an object like 3I Atlas, FMOST could have provided a time series of high-quality spectra throughout its approach, monitoring its compositional changes in exquisite detail without monopolizing the telescope's schedule. It makes the kind of dense, continuous data collection required to solve complex puzzles not just possible, but routine. FMOST, in tandem with Rubin's discovery engine and JWST's deep compositional analysis, represents the final piece of a new astronomical toolkit. We are no longer limited by our ability to find interesting targets or to study them in depth. We are limited only by our imagination in asking the right questions. This new capacity ensures that when the next 3I Atlas arrives, we will be ready not with frantic, ad hoc observations, but with a pre-planned, overwhelming campaign of characterization that will leave no doubt about its nature. While we gaze outward at an interstellar mystery, closer to home, NASA is wrestling with its own monumental challenge, returning humans to the moon through the Artemis program. The recent announcement that NASA is reopening the competition for the Artemis lunar lander beyond its initial single award contract with SpaceX reflects a tension between ambition and risk that directly parallels the 3I Atlas investigation. The initial plan to rely solely on SpaceX's Starship, a revolutionary but still developing vehicle, was a high-risk, high-reward strategy. Reopening the competition to include a second lander, potentially from a consortium led by Blue Origin or traditional aerospace giants, introduces redundancy, fosters competition, and provides a crucial backup, an insurance policy against potential delays or failures in the primary system. This decision, driven by both practical engineering concerns and political pressures, mirrors the choices facing astronomers studying 3I Atlas. Do you commit all your resources to a single, compelling explanation, the compositional model, or do you invest some effort in testing a riskier, long-shot hypothesis, the engineered probe idea, as a form of intellectual insurance? Both situations involve operating under profound uncertainty with high stakes. Artemis managers must decide how much schedule margin to build in, how much redundancy to pay for, and how much technical risk to accept. Too conservative, and the program becomes bloated and unaffordable. Too aggressive, and it risks catastrophic, very public failure. Astronomers face a similar resource allocation puzzle. Allocate too much of the world's telescope time to 3I Atlas, and you shortchange other vital science. Allocate too little, and you might miss the crucial observation that cracks the case wide open. Both endeavors, returning to the moon and deciphering an interstellar object, are test cases for how humanity executes complex, ambitious plans on the frontier of the possible. They require a blend of technical excellence, political savvy, careful resource management, and the resilience to persevere through inevitable setbacks. As the moment of truth approaches, it is time to soberly assess the weight of the evidence gathered so far. The conservative interpretation, the compositional transition model developed by Loeb and Keto, remains robust, parsimonious, and firmly grounded in established comet physics. It elegantly explains the timing of the jet reversal, linking it directly to the changing sublimation drivers as a function of heliocentric distance. The reported spectroscopic changes, showing a shift from CO2 to water-dominated emission, provide direct observational support. This model remains the default, most likely explanation, the one that requires the fewest unsupported assumptions. In the face of this, the engineered probe hypothesis, while intellectually thrilling and culturally captivating, currently lacks the requisite smoking gun. The absence of strong non-gravitational acceleration is its most puzzling aspect, but this can be explained by the object's sheer mass, a property independently constrained by the observed mass loss. The jet reversal, while abrupt, is not entirely without precedent in solar system comets that exhibit strong seasonal or hemispherical asymmetries in their activity. The history of astronomy is a long graveyard of supposed anomalies that later resolved into natural, if complex, phenomena. This history counsels patience, skepticism, and a strong preference for mundane explanations until the data forces otherwise. Yet, the very act of seriously considering the extraordinary hypothesis has immense value. It forces the scientific community to sharpen its questions, to design more clever and discriminatory observations, and to confront deeply held assumptions about what is possible in the universe. It pushes the technology of observation and analysis to its limits. The effort to rule out artificiality can often reveal new facets of natural phenomena that would otherwise have remained hidden. Whether 3I Atlas is ultimately confirmed as a natural comet or not, it has served as a powerful catalyst. It has acted as a fire drill, preparing our global scientific infrastructure, our analytical frameworks, and our very minds for the day when we may be confronted with an anomaly that does not yield to any natural explanation. It has expanded the Overton window of legitimate scientific inquiry, making it acceptable to ask, could this be artificial? And then to diligently work to answer the question, rather than dismissing it out of hand. The journey of 3I Atlas, from its discovery as a speck of light on a hyperbolic trajectory to its impending, transformative passage around the Sun, forces us to confront the most profound questions humanity can ask. Are we alone? Is the galaxy a teeming, vibrant network of life and intelligence? Or is it a silent, sterile expanse, with Earth as a singular, miraculous oasis? The confirmed discovery of even a single, derelict piece of extraterrestrial technology, a lone Voyager-like probe from a long-dead civilization, would answer that question definitively and forever. We would know that we are not the universe's only children, that the cosmic story includes other authors. The mere existence of an interstellar artifact implies that civilizations can arise and survive long enough to develop the capability to send their creations between the stars. This is a profoundly hopeful data point in the dark forest of cosmic evolution, suggesting that the great filter, whatever obstacle prevents life from becoming widespread and visible, is not necessarily absolute or immediately behind us. It suggests that the immense challenges of interstellar travel, which we view as nearly insurmountable, are not impossible. 3I Atlas may be a beacon, an intentional messenger, or it may be a piece of cosmic driftwood, an accidental artifact flung from its home system by a gravitational catastrophe. But its very presence, its very detectability, is a reminder that our solar system is not an isolated island. We are part of a dynamic, interconnected galaxy with a constant silent traffic of material, and perhaps, just perhaps, of messengers flowing through the space between the stars. The search for meaning in its passage is a fundamentally human endeavor, a testament to our insatiable curiosity and our deep-seated need to understand our context in the vast and seemingly indifferent cosmos. Regardless of its ultimate nature, the legacy of 3I Atlas is already secure, etched into the procedures and the psyche of the astronomical community. It has acted as a full-scale dress rehearsal for the new era of interstellar object science that the Vera Rubin Observatory will inaugurate. The protocols developed for its rapid follow-up, the coordination practiced between space-based and ground-based observatories, the data-sharing agreements tested under pressure, the very debate about how to handle high-profile, ambiguous anomalies, all of this has provided an invaluable learning experience. When Rubin discovers the next hyperbolic object, and the next, we will not be starting from scratch. We will have a playbook. We will know which observations to prioritize, which instruments to activate, and how to quickly distinguish a routine interstellar comet from something that demands our utmost attention. 3I Atlas is the herald, the first complex case that forced us to build the institutional and intellectual machinery needed to study its kind. It has taught us to look closer, to question deeper, and to never assume that we have already catalogued all the wonders and puzzles that the universe has to offer. It has shown that the boundary between known science and frontier speculation is porous, and that progress often happens precisely at that turbulent interface. The object itself will depart, but the lessons it imparted will remain, shaping the course of planetary astronomy and the search for extraterrestrial intelligence for decades to come. We are now in the final act of the immediate drama. The observations during and, most critically, in the weeks following the October 29th perihelion are the crucial data points that will make or break the competing hypotheses. The world's most powerful telescopes are pointed, their schedules cleared, their instruments calibrated. The global astronomical community is holding its collective breath, waiting for the data to stream in. Will the comet respond to the solar inferno as a natural body should, by dramatically increasing its outgassing, potentially fragmenting, and revealing a mundane, icy interior through its death throes? Will its astrometric path finally show the clear, unambiguous signature of non-gravitational acceleration, confirming that its outgassing does indeed produce thrust, just in a complex, previously hidden way? Or will it pass through the crucible with an uncanny, unsettling stability, its jets modulating not with chaotic violence, but with a precision that continues to whisper of control and intention? The close approach to Earth on December 19th provides a final, precious window for a detailed close-up. The data collected in the period between perihelion and Earth approach will be pored over by thousands of scientists across the globe. The papers will be written, submitted, and fiercely debated. Conferences will hold special sessions. A consensus, one way or another, will slowly emerge from the cacophony of analysis. The story of 3I Atlas is rushing towards its climax, driven by the immutable laws of orbital motion and the relentless pursuit of human curiosity. In the end, as we await the verdict from the data, we are left with a fundamental choice about how to listen to the cosmos. Do we adopt a stance of extreme conservatism, dismissing faint, ambiguous signals as noise, lest we be fooled by randomness and wishful thinking? Or do we consciously choose to lean in, to invest significant effort in the long shot, terrified not of being temporarily wrong, but of the eternal, existential cost of missing a signal that was real? This is the core asymmetry that justifies the entire technosignature search and the intense scrutiny of objects like 3I Atlas. If 3I Atlas turns out to be a perfectly natural comet, which is the overwhelming likelihood, we have lost nothing but a relatively small allocation of telescope time and intellectual effort. In return, we gain a far deeper understanding of the diversity and behavior of interstellar comets. We have stress-tested our observational networks, and we have advanced the science of cometary physics. It is a net win for knowledge. If, however, it is artificial, and we had failed to look, if we had dismissed the anomaly out of hand as too speculative, we would have lost everything. We would have missed the chance to know that we are not alone, to potentially learn from a technology millennia or millions of years beyond our own, to have our cosmic solitude forever and definitively broken. The potential loss in this scenario is incalculable. Therefore, the choice is clear. We must look, we must question. We must dedicate a portion of our resources, no matter how small, to the pursuit of the extraordinary. We must follow the evidence, no matter how strange the path may seem, with rigor, skepticism, but also with the courage to entertain revolutionary possibilities. This is the only rational choice for a species that wishes to know its true place in the universe. The story of 3I Atlas, in its entirety, is a perfect microcosm of the grand scientific adventure. It begins with a single, baffling observation, a tale pointing the wrong way. It spirals out into a global collaborative effort, involving the most advanced machinery and the brightest minds our species has to offer. It is debated in the refined language of academic journals and the chaotic forums of social media, in the hushed halls of great universities, and in the living rooms of curious people everywhere. It forces us to confront the limits of our knowledge and the breathtaking breadth of our imagination. Whether this specific object turns out to be a peculiar iceberg from an alien ocean or a silent ambassador from a distant civilization, it has already succeeded in one profound way. It has expanded our horizons. It has shown us that the universe is capable of surprises that challenge our most fundamental categories and force us to rethink the possible. In that uncertainty, in that fertile and exhilarating space between the known and the unknown, is where true discovery lives and where the future of our understanding is forged. For all our advanced technology, for all our complex equations and sophisticated computer models, the story of 3I Atlas is, at its heart, a story about the human gaze turned upward. It is about an innate, unquenchable curiosity, a need to understand the lights in the sky and what they mean for us. For centuries, comets were omens, portents of doom or divine messages, feared and revered. Today, they are data points, subjects of physical inquiry. But as 3I Atlas demonstrates, they can still carry messages, not from gods, but from the cosmos itself. Messages that have the power to shake our civilization to its very core. The scientists meticulously tracking its path, the engineers who designed and built the telescopes, the programmers who wrote the data analysis pipelines, the public captivated by the mystery. We are all part of this same ancient and uniquely human project. We are the universe's way of becoming aware of itself, and in studying a visitor from the interstellar abyss, we are, in a very real sense, studying a part of our own extended cosmic family, a piece of the great story of which we are also a part. And so, regardless of the outcome, 3I Atlas will leave. After its close approach to Earth in December, its brightness will inexorably fade as its distance from the Sun increases and its activity wanes. It will race out past the orbits of Jupiter and Saturn, growing ever fainter, a dwindling speck of light. Within a few short years, it will be beyond the reach of all but the very largest telescopes on Earth. Then, it will be gone, vanishing completely into the interstellar dark from whence it came, its secrets perhaps forever locked within its retreating form. It will continue its endless journey for millions of years, through the great void between the stars, until it perhaps one day encounters another star, another planetary system, another set of eyes to look up and wonder at the silent, mysterious traveler from a sun they will never know. The work does not end with the departure of 3I Atlas. The Vera Rubin Observatory will come fully online, its great eye opening to the sky. The lessons learned from this episode will be codified into software and observing protocols. The next alert of a hyperbolic object will come, and then the next, and the next. The search is perpetual, the vigil is eternal. The universe is vast beyond comprehension, and we have only just begun to listen, to truly pay attention to the traffic passing through our celestial neighborhood. 3I Atlas was a test, a preparation, a trial run for our minds and our machines. The real discovery, the one that will irrevocably change everything, may still be out there, right now, hurtling toward us in the silent dark, waiting for the moment we are truly ready to see it for what it is. As the final data from the perihelion and Earth approach campaigns are analyzed, one question will inevitably remain, echoing in the halls of science and in the public imagination. What was it? The answer may be a series of definitive, peer-reviewed papers, concluding with high confidence that it was a layered comet with an unusual but perfectly natural sequence of volatile sublimation. The mystery will be solved, the file closed, or the answer may be a lingering, unresolved anomaly in the astrometric data or a peculiar spectral feature that resists all conventional explanations. It will become a ghost in the machine, a footnote of curiosity for future astronomers to ponder when the next such object is found. Or, in the most extraordinary of all possible futures, the answer may be a signal we finally managed to decode, a message from the void that we are only now learning to read. The story is not over until the last datum is analyzed, and even then, it may only be the end of a chapter. This is not the end of the story of 3I Atlas. It is rather the end of the beginning. Its passage through our solar system marks a watershed moment, the point at which our species graduated from one that merely inhabits a single world to one that actively, systematically, and intelligently searches the galaxy for company. For clues for context, we have built the tools: Rubin, JWST, FMOST, LIGO. We have developed the methods: multi-messenger astronomy, rapid response protocols, technosignature detection criteria. We have asked the question aloud in the serious forums of science: are we alone? The universe has heard us. Now we wait for the reply, knowing that we are finally listening closely enough, and with the right intent to understand it when it comes. And so, we keep watching. We point our telescopes at the sky, night after night, generation after generation, scanning the darkness for the next flicker of light that doesn't belong, the next trajectory that doesn't fit, the next visitor that challenges everything we think we know. The story of Three-Eye Atlas is both a promise and a warning. The promise is that the universe is stranger, more complex, and more wonderful than we can possibly imagine. The warning is that we must be ready, intellectually, technologically, and spiritually, for the day we discover we are no longer alone. The vigil continues, not as a passive watch, but as an active, relentless search. The sky is full of secrets, and we are just learning how to listen. The greatest story ever told is still being written, and the next chapter could be revealed at any moment, with the next alert, the next image, the next strange visitor from the boundless dark.